Good morning, all of you. Today we are discussing numerical solutions of algebraic and transcendental equation. First, we have to know what do you mean by transcendental or algebraic equation. An expression of the form of this, where a0 not equal to 0 is called a polynomial of degree n, and the polynomial fx equals to 0 is called an algebraic equation of nth degree. If it is an less than n, that is if value of n equals to 2, so it is called second degree polynomial. If n equals to 3, it is called third degree polynomial, and so on. If fx contains trigonometric, logarithmic or exponential functions, then fx equals to 0 is called a transcendental equation. That means if in this equation any trigonometric function, that is sin x, or exponential functions or any logarithmic functions will be included, then that type of equation is called transcendental equation. If fx is an algebraic polynomial of degree less than equal to 4, then we have some direct methods for finding the roots of such an equations. But if fx is of higher degree or it involves transcendental functions, then direct methods does not exist, and we need to apply numerical methods to find roots of the equation fx equals to 0. Some useful result: when alpha is the root of the equation fx equals to 0, we know f of alpha equals to 0. Every equation of nth degree has exactly n roots. It may be real or may be imaginary. That means if any equation has third degree, that means it has exactly 3 roots that may be real or imaginary. We have one theorem which is called intermediate value theorem. It states that if fx is a continuous function in a closed interval ab, and f of a and f of b are having opposite signs, then the equation fx equals to 0 has at least one real root or odd number of roots between a and b. And if fx is a continuous function in the closed interval a comma b, and if a and if b are of same signs, then the equation fx equals to 0 has no root or even number of roots between a and b. So this is the clarifications of transcendental or algebraic equation. Next, we are discussing numerical methods to find algebraic and transcendental equation. Normally, here we are using iterative procedures. Most numerical methods use iterative procedure to find an approximate root of an equation fx equals to 0. It requires an initial guess of the roots as starting value, and each subsequent iteration leads closer to the actual root. And this is a formula for order of convergence. Order of convergence means for any iterative numerical method, each successive iteration gives an approximation that moves progressively closer to the actual solution, which is known as convergence. And this is the formula of convergence. First, we have so many methods to finding out the roots. Number 1, bisection method, Newton-Raphson method, Regula-Falsi method. Here we are discussing bisection method. Bisection method is used to find the approximate root in an interval by repeatedly bisecting into subintervals. If this is an interval, after bisecting, we get a root in the middlemost position. And again, we can bisect this portion or this portion, and again we root an approximate root. And repeatedly bisecting into subintervals, we get the exact root. It is very simple and robust method, but it is also relatively slow. Because of this, it is often used to obtain a rough approximation to a solution, which is then used as a starting point for more rapidly converging methods. This method is based on the intermediate value theorem, which is already discussed in the last slide, for continuous function. What is the algorithm of the function? If the function fx is a continuous in the given interval, what is the condition? F of a and f of b are of opposite signs. That means if f of a greater than 0, f of b must be less than 0, or if of f of a greater than 0, f of b less than 0. And after that, multiplying these two functions, we get negative value, that is less than 0. Now, first step is after guessing the initial approximation, we have to find out the initial root by taking a plus b by 2, which is the one of the 3 conditions of finding out the first approximation of x1. After that, after getting x0, we have to put in the function and find f of x0 equals to 0. Then we have a root of the function at x equals to x0. Then again we have to use the condition, since x0 is lie between a and b, then we have to again find if f of a dot f of x0 is less than 0, or f of b and f of x0 is less than 0. If this condition has been satisfied, then between these two again we have a root, or if this condition has been satisfied, then again we can have one root. So continuing this process, we can find the desired degree of accuracy. Here is some remarks. Convergence is not an unidirectional, as none of the endpoints is fixed. As a result, convergence of bisection method is very slow. And repeating the procedure n times, the new interval will be exactly half the length of the previous one until the roots is found of desired degree of accuracy. Here we have taken an example. This is my fx. So fx equals to, then first we have to start from the 0, that at 0 the functional value is positive or negative. So f0 is negative and f1 is positive. If f1 is another value as negative, then we never tell about that roots lie between 0 and 1. Since f1 is positive and it will satisfy f0 dot f1 less than 0, that means fx is continuous in this interval and at least one root exists in this given interval. Now as an initial approximation, we have to find taking a equals to 0, b equals to 1. So we are applying the formula so that we are getting x0. After getting x0, the value is 0.5. We have to find the functional value. If functional value less than 0, and again if is 0.5 and f1 less than 0, that means we should take the first approximation. In the first approximation, a equals to 0.5 and b equals to 1. B will be fixed here because this value is negative. This value is negative. And which value is negative? a0. That means this value is negative. If we are negative will be coming out throughout the steps, then b will be fixed and a will be changed. In the next approximation, again we found functional value negative, so a will be changed, b will be fixed. In x2 we are getting positive 1, so now a will be fixed, b has been changed, b should be the new roots, that is on x2. And proceeding in this way up to some approximations, here we have to calculate 7th approximation. In the 7th approximation the value is 0.8633, and in 6th approximation value is 0.8672. That means up to 2 decimal places it has been stabilized, and hence 0.8633 is the real correct root to correct up to 2 decimal places. So at least if a question is you have to correct up to 2 decimal place, so 2 decimal place will match for the last last two approximations. Again we are discussing another example. Here fx equals to this, correct up to 2 decimal places. So if you can start using 0 and 1 also. Here we are taking 0.5, which gives us negative, and at 1 it will give the functional value positive. That means rules lie between 0.5 and 1. So a0 is taken as 0.5, b0 is taken as 1. So x1 is a0 plus b0 by 2, that is 0.75. Now f of functional value at the new root is equal to this. Therefore root lies between 0.75 and 1, and also we are getting the positive value. So in the next table we are calculating that this value is the a0, b0, this is x1, taking n equals to 0, and functional value is positive. If functional value is positive, and then our positive root will be changed. That means new root should be taken as positive. New root should be taken as in this column. Similarly, and this will be fixed, this has not changed, this will be taken as earlier. So now this is my new interval. Again find out the new root. Again functional value is negative. If it is negative, that means new root should be go for less than 0 function. That is, this is can be taken as a0, and b0 will be fixed. Again take the formula a0 plus b0 by 2, like that, and we are getting 0.687. Again we are getting positive. So if this value is positive, so positive column will be changed. So in positive column the new root will be taken, and this will be the remain same. In this way we proceeding up to 7th approximation. The roots are first place are equal, and second is the decimal place 6 to 8 and 6 to 6. That means approximately we have to correct up to second decimal place, we are getting 6 3. So the root up to 2 decimal place is required, that is equal to 0.63. Thank you.